Good
Good
evening, everyone.
evening. Good evening, everyone. My name is Tequila Smith. I'm founder and executive director of Science, Engineering, and Mathematics Link Incorporated, and I want to welcome everyone to our Teen Science Cafe. Our Teen Science Cafe is a program of our Math and Science Career Academy, and the purpose of this program is to provide teens with the opportunity to meet and interact with STEM community to learn about STEM careers as they're making important decisions about college and career in middle and high school. So, without further ado, I'm going to bring our program coordinator, Carlin Pounders, on to introduce tonight's speakers for the cafe.
Hello again, everyone. So tonight we are in for a treat because we have two speakers. We usually have just one. We have Tony Bujana, who is an electrical engineer working in the commercial aerospace industry. He has been at his current role for over 4 years. Before then, Tony went to a small engineering school in Longview, Texas, where he received both his master's and undergrad in electrical engineering. Zaire Silvia is a systems engineer working in the military aerospace industry. She has been an engineer for 4.5 years. She attended Tuskegee University for aerospace engineering, and she'll be graduating from Johns Hopkins University for space systems engineering in December of this year. So without further ado, I will hand it over to our speakers.
Thank you. And good evening, everyone. I am Zaire Silvia, that was as mentioned earlier, and this is The Sky is Not the Limit by Zaire and Tony will give his introduction now.
Thank you, Zaire. Thank you, Carlin, and thank you, Tokiwa. My name is Tony Bujana. I am an electrical engineer in Collins Aerospace. I am originally from Venezuela, South America, which, if you didn't know, is that little country over there that is a little far from the States. I grew up there speaking Spanish and playing tennis. And then I came here right after finishing high school in Venezuela. You might be wondering, how does someone from Venezuela ends up in the States? Well, I got to give a lot of credit to tennis. I received a scholarship to attend LeTourneau University, which is a small engineering school in Longview, Texas. And I always knew I wanted to be an engineer, but I wasn't sure what kind. Right after high school, before starting college, I read an article about technology, and I got really interested in applying technology to the health field. So I started out as a biomedical engineer. Towards the end of my freshman year, as I was taking all my introductory classes in electrical engineering, biomedical engineering, and all that, I got really interested in the field of electronics. So I decided to double major. I pursued that double major, and I completed my bachelor's in biomedical and electrical engineering from LeTourneau University. Then I decided to stay an extra year to also finish my master. After that, I got an offer to come work for Collins Aerospace here in Iowa, and I have been here for the last 4 years. Even though I did work a little bit on biomedical engineering projects back in school and electrical engineering projects as well, right now I am 100% a hardware guy. I work purely on electronics. And that is a little bit about me. I'm gonna let Zaire introduce herself now.
Thanks, Tony. As everyone knows, my name is Zaire Silvia. I'm originally from Denton, Texas. It's about 45 minutes outside of Dallas, Fort Worth, on your way to Oklahoma. I attended Tuskegee University, where I majored in aerospace engineering. And Tuskegee University is a historically Black college and university, and it is the #1 producers of African American aerospace engineers in the country, as well as it has a long history of Tuskegee Airmen and a few other amazing engineers, and also a great many innovators as well. So I would encourage everyone to go research Tuskegee University. And with that, I ended up moving to Iowa, where, just like Tony, I moved to Cedar Rapids, Iowa for Collins Aerospace. And with that, while I was here, I wanted to get a master's degree in space systems engineering from Johns Hopkins because I love space. I love the solar system. I love anything that goes super fast. And it just gives me a little bit of excitement every time I think about it. And as a systems engineer at Collins Aerospace, I do work on the military avionics side. My first job when I first started was in communications engineering. So it's mostly anything that deals with radios. And then now I work on the avionics side where it deals with anything that's on the cockpit of the aircraft. So I work with navigation tools, which is really fun for me. And thanks for learning a little bit more about me. But I think it's time for you to learn a little bit more about Collins Aerospace.
From the smallest details to the highest pursuits, we are redefining aerospace. With our customers, we relentlessly tackle the toughest challenges in our industry. And every day, we imagine ways to make the skies and the spaces we touch smarter, safer, and more amazing than ever. Together, we chart new journeys and reunite families. We protect nations and save lives. And we explore the unknown. We believe in the power of intelligence and partnership to guide our customers into the future, reshaping our industry across the globe and even beyond. The paths we pave together lead to limitless possibility, and the bonds we form propel us all higher, again and again. We are constant in our evolution. We are connected to our customers, always. We are compelling as we boldly step forward. We are redefining aerospace.
So that is a little bit about the company that me and Zaire work on. But what do we actually do? What does an electrical engineer do? I'm gonna play a quick video that tells you what an electronics or electrical engineer do.
What is electronic and electrical engineering? Electronic and electrical engineering combines design creativity with scientific concepts to develop new electrical products, applications, and systems. But what does this really mean? It's designing new types of electronic materials and integrating these into systems. It's advancing healthcare by developing complex biosensors. It's researching systems, control, and propulsion for robotics and autonomous systems. It's developing better power distribution systems for renewable generation in electric vehicles. Electronic engineers are making more efficient, powerful, and universal electronics. Are these things you want to achieve? You might become an electronic engineer if you like combining maths and science, implementing new solutions, designing, building, and testing systems, using your knowledge in business environments, developing new ideas into usable products, taking your practical skills out of the lab and into the world. Studying electronic and electrical engineering involves learning theory in lectures, applying what you learn in practical lab sessions to real-world problems, solving challenging mathematical engineering problems, exploring new technologies, designs, concepts, and products, developing industrial strategies, understanding how to design systems, from materials to circuit architectures and system hardware, working in teams to solve global engineering challenges. By doing these things, you'll gain more than electronic engineering theory. You'll have skills in critical thinking, problem solving, project management, and business acumen. You can work in industries like electronics, avionics and space, robotics, automotive, and information technology, preparing you to make an impact on the world sustainably.
So as you can see, electrical engineering is a very, very big field. Everything that has a screen or uses electronics there is an electrical engineer behind it, whether it is your toaster, your cell phone, your TV, or an airplane. I will tell you a little bit about the area of electrical engineering that I work on, and that is avionics. Avionics has two different categories. Commercial avionics, which is your passenger aircrafts, and is the type of planes that people go to for vacation, business trips, and the customers for that is usually the airlines that we are all familiar with. But then you also have military avionics, and that is those fighter jets. Then the customer for those are usually governments. I am 100% involved with commercial avionics. And what are the parts of an airplane? As you can see, there are a lot of different parts that work together to keep the airplane flying safely. We have the flight deck, which is what the pilot uses to control the aircraft, to fly up, to go faster, etc. You have the wings, which is purely a mechanical structure, but you also have a lot of electronics inside the aircraft itself. On cabin system, for example, where you have your seats, etc., you also have in-flight entertainment. You have those touch screens where you can see movies, etc. And you also have the tail of the aircraft, such as the horizontal stabilizer. My main expertise is in cabin system and in the horizontal stabilizer. And I'm going to tell you a little bit about the horizontal stabilizer. It is this on the right picture, on the picture to your right, it is that rear part of the aircraft, kind of like the tail of the aircraft. And what it does is that it controls the altitude or the height of the aircraft. As the pilot uses the controllers on the flight deck, it makes the plane go higher or lower. As you can see, there is a lot of safety standards that go into this. And I'll give you an analogy. Imagine that you're watching a movie in your cabin and something fails out of nowhere. Unless it was your absolute favorite movie and you've been waiting to see it for a long time, in a week from that day, you're most likely going to forget that your cabin or your in-flight entertainment fails. But if something on the horizontal stabilizer were to fail, that could mean lives. That's why that system needs to be very, very, very safe, very robust, and failure-proof, pretty much. So how does the pilot command the horizontal stabilizer, and what role do electronics play in this? It's magic. All we do is magic. No, I'm joking. It's not all magic. If we actually look at the picture to the left, we can see the controllers of an aircraft. As the pilot presses those controllers and uses them, you have an electronic box that receives those signals from the controllers that the pilot uses. That electronics box processes that signal, and then it drives a motor, and then that motor in turn moves the stabilizer. To give you an analogy of a simpler system, imagine the window in your car. As you press the button, that emits a signal that eventually moves a motor, and that motor rolls down or up your window. To give you another analogy, imagine you're using your cell phone, and you are the user of the cell phone, just like the pilot is the user of the airplane. As you press your cell phone controllers, for example, if you're typing and you press the letter T, then that CPU in your cell phone receives that signal from the letter T that you are commanding. And then it processes that signal and it outputs another type of signal that is the actual letters that you're typing. That is the same principle that is used in an aircraft. As the pilot uses the controllers, an electronic box receives those signals, and then it outputs a different kind of signal. In this case, is to control a motor and a stabilizer. And this is a little bit of the electrical engineering field of avionics and about a system that I work on. Now, Zaire is going to tell you a little bit about systems engineering.
Thanks, Tony. And as with systems engineering, we're going to watch a short video about systems engineering.
Systems engineering is a science applicable to the development and maintenance of highly complex products like trains, cars, airplanes, power plants, computer chips, and spacecraft. The goal is to federate all of a product's behaviors into an efficiently functioning unit. For example, the human body requires a respiratory system to inhale and transfer oxygen, a circulatory system to send this oxygen along with nutrients to our cells, and so on. Even small changes in one system could impact another system, and if one of them fails, so could the body. Companies are thus using systems engineering software that includes requirements management modeling, simulation, and test tools to develop products as sophisticated and smart as the human body. Let's look at a car and its requirements to better understand. Versus the time when innovative cars were simple enough for one engineer to design them. Remember the famous engineer, Mr. Benz? Today, hundreds of engineers must work together to make innovation happen. Already today, you're driving around in a kind of supercomputer. Everything from engine performance, power distribution, climate control, fuel usage, and safety functions are controlled by an intricate system of networked electronic chips and millions of lines of software code. Très compliqué. Traditionally, a separate department designs and engineers each system. Only when you consolidate the systems can you test what happens to the whole when a part malfunctions and make adjustments within context. Too late sometimes. Then there are regulatory requirements. Complying with them increases production costs, like for planes, where certification bodies must run traceability tests and examine every last detail of your system's digital intellectual property. Today, thanks to systems engineering software, all of this can be done faster at a lower cost and more efficiently. Companies can, for example, use it to produce fully documented safety evidences directly from the virtual model. Also, because modern systems engineering software encapsulates work within a single interoperable platform, teams naturally federate and collaborate. Isn't that great? Finally, manufacturers can safely tuck away digital versions of their packaged engineered systems for reuse come next car design cycle. This is brainy stuff, huh? Smart all the way around. Thanks, Collaborative Systems Engineering. Stay tuned to the Elementary Collection for more animated discoveries.
Now that you know a little bit about systems engineering, there's a few different phases that we use. We have 6 phases for systems engineering. The first phase is to identify the problem. With most items that we work on, we have to figure out what's the problem or is there an upgrade that's needed. The second phase is existing solution. Is there an existing solution? Similar to the video says that can we reuse something that we already created and maybe improve on it? Or is it something completely from scratch that we need to create new requirements for? Phase 3, we have to define the object. What are we going to update? What are we going to create? What are we going to prototype? With phase 4, we got to have proof of concept. Basically, what are we doing? And then phase 5 is our prototype, so an actual item for us to test and make sure that it works. And our phase 6 is results, and we're done. But that sounds simple, but there's a lot more steps in between each different phase. For aerospace, if we have an aircraft, most aircrafts we know, okay, they can fly now. But if we need to upgrade them because of something that a pilot might have told us that says, hey, if you can do this, this would make my life a little bit more easier. Or think this is a really cool feature. Could we add that onto the aircraft with the next upgrades? And with that idea is how we go into our current systems engineering, at least with my job. So on a daily basis, I might get a customer that comes in and says, hey, I want to change the buttons for us to press where we can log in our point A to point B navigation. And then with that, we're like, okay, let's go talk to our engineers. And with a systems engineer, I can't just do everything by myself. I have to work with other engineers like Tony and our mechanical engineers and our software engineers to identify the problem and can we actually implement this problem. And then after talking to the other engineers, figure out, okay, maybe we can do this. And then we'll go back to the customer says, yes, we can do this for you. And then we'll give them our requirements on what we need to do to complete this. And after that, we'll come back to our table and into our in-house where we'll create an existing solution or we'll create new requirements. And if it's an upgrade to something on the aircraft, we might have something that we might have already done to another customer, or if not, we'll create something new for them. And with that, we'll go into defining our objectives. Okay, so if the pilot wants our screen to be blue instead of green, how would we implement this? And then after that, we have to have proof of concept. So if it is going to change from blue to green, then our software engineers has to create that software for us, well, the code for us to change the screen color. And then we'll go into the lab. Well, first we'll go work on our personal laptops and computers, have a mock-up simulation on our computers and see if it actually works. And then we'll actually go into our lab. And our lab is a setup simulation of an actual aircraft, but it's only the controls area where the pilots fly. And then we'll go upload software there and see if it actually works, and we'll try to fly the plane with the new upgrades. And then after that, we'll go into our different test events. So with us, we have a blue label, red label, and a black label. Our blue label is our initial proof of concept. And this is basically us going into and creating the new software or new upgrades. And then we'll go out and test that on our personal computers. And then we'll even go into the lab for a little bit as well. And then with our red label, we'll go into the lab and actually do an official test event to make sure that we got all of the kinks out. And then with that, we'll package that up and send it off to the customer so that they can do a flight test. And during this time, they're actually flying the aircraft and testing out the new upgrades and to see if it's actually working and seeing if there's any hiccups along the way. And if it comes back great, which we really hope every time it comes back great, we can release it into our black label, which is the official upgrade, and that's our results. But if it doesn't come back great and they give us some issues, then we'll go back to the drawing board and try to figure out how can we edit this problem. And that explains systems engineering in a nutshell. But I think it's a great time for everybody to become an engineer today. So let's go become an engineer. Next slide, please. Okay, so our scenario today is a customer is requiring a circuitry to control one light bulb, and you must use one battery, and the maximum power allowance is 4 watts. So how do we use this, and how do we define what we're going to go to achieve? Well, first of all, we have a customer, we have a team engineer lead, and we have engineers. Well, congratulations, everyone. You have officially become an engineer. Your responsibilities are to make sure that the project actually meets the requirements, so the scenario requirements. And you're also responsible for making sure that the development of the light bulb actually becomes real. For your team engineer lead is Tony. He's going to be the person that communicates with your customer as well as communicates with your engineers to make sure that we're all in communications and we're all making sure we're meeting the requirements to make sure to have the prototype and the results at the end. And I am your customer. And I'm going to provide you requirements and any questions and answerings about the design that I can help with. And now we have to go into our different phases. So phase 1, we got to identify the problem. And our problem is that I'm the customer and I require a circuitry to control one light bulb. And the one light bulb must be one battery, and the maximum power allowance is 4 watts. In your phase 2, you have to look at existing solutions and requirements. Are there existing solutions? No. Is there existing requirements? Yes. So these are your requirements. Control means toggle on and off, and toggle means switch. This is just an engineering term that we use. Power is equal to voltage times current, and basically that just means that you're going to get power with those two things multiplied each other. And you also need to go download this link right here for you to participate in this activity. So I'll give you a few minutes to go download it. It's really just, if you click on the link, it will take you right there. And while we're waiting, we'll go to the next slide, which is phase 3, and Tony will talk about that.
Thank you, Zaire. So phase 3 of the design process is when we define our objectives. So as Zaire mentioned previously, our customer is requiring a circuitry to control one light bulb. The circuitry must use one battery, and the maximum power allowed is 4 watts. So usually, when you get a statement like this, you need to make sure there are no general terms, or there is no confusion on what the terms mean. Control could mean varying the intensity of the light bulb, more brighter, less bright, or it could mean just controlling by turning it on or off. So I go back to my customer, Zaire, and I ask her, Zaire, control in this case means on or off, and that is the definition we're going to use, and I expect to get approval from the customer. So to control a switch, a light bulb on or off, you usually need a switch as the button to press it. And then for the second requirement, which is that it must not exceed more than 4 watts power, we have our voltage and our current. That is the engineering parameters that we work with when designing this circuit to control the power. We also need to define what components we need. We need a battery, which is part of the requirements too. We need resistors, because resistors is what we use to control the current in a circuit, in a simple circuit such as this. We're going to need a switch, and of course, we're going to need a light bulb. And our last objective is to make sure we have a simulator working for this exercise. So if you click on that link, it will take you to this simulator that you see over here. Okay? So there are a lot of good things that we can do with this simulator. The first, we can grab a battery, we can grab the light bulb, and if we just grab wires and connect those two together, we immediately see how the current starts flowing and how we get the light bulb on. But are we meeting the requirements right now? Requirements were no more than 4 watts, control the light bulb, and use one battery. We have one battery, but right now we don't even know what power is. How do we measure power in a circuit? Remember, I mentioned previously we need to measure the current as well, and we need to measure the voltage. So we're going to go ahead and break this connection over here and add this lab instrument, which is called an ammeter. The ammeter measures the current going through it. And right now we can see that we have 0.9 amps of current going through the circuit. And using this instrument, which is a voltmeter, we can actually measure the voltage, which the battery is already telling us what the voltage is. But just so you know, in the lab, you're going to need a voltmeter to measure your volts. So this is the circuitry right now. We have 0.9 amps and we have 9 volts. Is this meeting our requirements? We don't know yet, because all we did was open the simulation and connect some things. And that is different from what engineers usually do. Engineers usually do some math, design their circuit, and then they go and pick their parameters. But I wanted to show you how the simulator works first, so you're familiar with it. So now we're gonna go into the next stage, which is proof of concept, where we design the circuit. I know this may seem like a lot of boring math, but stick with me. It's just two simple equations, okay? We have that power is equal to voltage times current, as Zaire mentioned previously. So let's start plugging in the values that we know. We know that our circuit must be less or equal to 4 watts. So we plug in that there. Power equals to 4 watts. We know that we are going to need to use just one battery, and we're going to use a 10-volt battery for this. So with that, we can plug in 10 volts for the battery. And hey, what do you know? Now we only have one unknown to solve for, which is the current. So we have 4 watts equals to 10 volts times current. Solving for current, we get that it is equal to 4 watts over 10 volts, and that is equal to 0.4 amps. If you remember previously, that's a little different from what we're measuring in our circuit. Now, how do we get the circuit to output 0.4 amps now that we know what the value needs to be? This is where the second equation comes into play, and that is that voltage is equals to current times resistance. We already know what our voltage is. Our voltage from using one battery is going to be 10 volts because we're going to select a 10-volt battery. And we found what our current needs to be, 0.4 amps. So now we just got to solve for resistance. When we solve for it, we get 10 over 0.4, which is equals to 25 ohms. So we know what this needs to be. It needs to be a circuitry with a 10-volt battery and a 25-ohm resistor, so that we can get 0.4 amps. So we're gonna move back to our simulation over here on our previous circuitry. Okay, right now it is 0.9 amps. We're gonna add this component over here, which is a resistor. We're gonna connect our circuitry to the resistor and to a light bulb, and we get current flowing again. Wait a second. Oh, this is 9 volts, and we designed this. We said the circuit was going to use a 10-volt battery, so we got to change the battery. If we double-click on it, we can increase it to 10 volts. Okay. All right. So now we have 10 volts, and we have 0.5 amps. That is still a little higher than the 0.4 that we require, but we don't have the correct amount of resistance. We have 10 plus 10. As you can see, 10 from the resistor and 10 from the light bulb, that's equals to 20. So if we increase the resistance here from 10 to 15, so that it gives us 15 plus 10 is 25, and we use a 10-volt battery, we get the 0.4 amps that we need. And this effectively gives us a circuitry with a light bulb that uses no more than 4 watts. Now, are we meeting all the requirements? Let's go back to our previous screen. Remember that we need to be able to control that light bulb. We have our battery, a resistor, a light bulb, but we don't have a switch yet. So we're gonna need to go back here and find out where to control it. And if you look on your menu from your left, you'll see that you have a component here called a switch. So if we break this connection over here and add the switch, now it's open, the circuit is off, the light bulb is off, and we can turn it on. So we effectively now have a simulation of a circuitry that controls a light bulb on, off, and it produces no more than 4 watts. Why do we do simulations? Because we're able to effectively prove that the previous math or the design that we did is correct, and also is safer. When you go into a lab, if you try just connecting light bulbs to batteries, bad things could happen if you don't know what you're doing. So this is why I encourage you all not to do any of these actual experiments in real life, and only do it on a simulator so that you don't get hurt. Now, if we go back to our design process, we know that our math and simulation works. The next step is prototypes. we already know a concept, our proof of concept works. The next step is prototypes. We're not going to actually build a prototype because we don't have the components and we cannot build it right now. But in this stage is when once you prove that your circuitry works in a simulator and with your math, then you actually build it and ensure that it works just as well in real life. Because usually math and simulations get you very close to what the real world does, but it's not 100% precise. And this is the link again that we use for our simulator. This is the basic circuitry that we built. Once your prototype works, you go and you have your results. You effectively go back to the customer and you tell them, we have this design. It controls the light bulb. It's able to turn it on and off. It uses this switch. It uses this battery. And it produces no more than exactly 4 watts. So it meets all your requirements. And this is the design process that we engineers usually do. Again, I need to encourage you not to try any of these experiments in real life. Just stick to the simulators, because if you don't have the training required, people could get hurt using those components. But I do encourage you to play with the simulator and learn a little bit about how circuits work, because all these basic components, resistors, switches, batteries, those are the very basic components that you later on get to implement in very big circuits in electrical engineering. And that is the design process for engineering. And now we're gonna open it up for any questions that you may have.
Well, while we're waiting for questions to get in, Tony, what was the reason why you became an engineer?
I became an engineer because I always liked math, and I wanted to be able to use math to help people and improve their life and make life a little safer. And that was the way to do it. I wanted to make sure to use the skills that I have or the things that I'm interested on, and to help people and make sure that the instruments that they use are safe. And when it comes to the avionics industry, you really need to make sure to be precise and that all the components are safe in the aircraft. What about you, Zaire?
Well, I wanted to become an aerospace engineer because I wanted to become an astronaut, actually. I loved space since I was a child. Even with my dollar store telescope, I would go outside and tell my mom all about the constellations and the planets. Even though I didn't know exactly everything aerospace engineers did when I was 5, but I learned. And eventually I came into aerospace engineering because with my research from astronauts, I was able to see that a lot of them had aerospace engineering degrees, and then they went on to getting a master's and maybe a doctorate, depending on what field of expertise they wanted to get. And with me not being an astronaut right now, I decided to go get a master's in space systems engineering so that I can still have fun with space and hopefully switch over jobs into more of the space industry as well.
That is awesome. Carlin, do we have any questions?
Let's see. So we're still waiting for some to come in, but I did have a question about actually what Zaire just mentioned about wanting to work in space. In my research, I saw that space tourism is something that's trending, particularly for aerospace engineering. So could you guys talk about any other trends that you guys know of for aerospace engineering?
I'll go first. Right now, they have space mining that they really want to do in the future, where they want to mine on an asteroid. So we have to figure out how to get a spaceship or a spacecraft to the asteroid and actually have a probe where it's going to mine the materials on that asteroid and then send it back to Earth. This idea is still works, and it's going to take a couple of years. I might not even see it in my lifetime, but it could. You never know. But that's really exciting, and I know that I did a research paper on that for one of my classes. And I was really excited about that, as well as trying to 3D print a actually 3D print like beef in space. It's really interesting. So this actually idea came out last year in 2019 about how you would 3D print an actual meat in space, because in space they normally just have everything suction proof, so they don't have like real meat out there where they can cook on a frying pan. But this is one way where they can get protein.
Wow. Sounds pretty interesting. Another question is, when you guys were talking about the phases, typically how long does it take, for something like that? Because I would imagine that it takes a while, but I might be mistaken. How long does it take?
Well, it depends on the program. You have programs that are a 3-year program, and then you have longer programs. We usually have a deadline, and depending on how many engineers you have working on it, you can go a little faster. But in avionics, you have a lot of standards that you need to meet, and a lot of steps where you check to make sure that you're following all the requirements and that you're following all the industry standards to make sure there are no errors and that you're following all the safety protocols. So depending on the program, it could take a long time from the time that you get the requirement from the customer, and then you break it down to the objectives, and then you do your proof of concept, and so on. And then from the time that you design it, then there is a lot of documentation that follows after you actually have a working circuit, because you gotta document and prove that there is nothing wrong with the circuit that you are working on. So depending on the program, it could take from 3 years to longer.
Wow. And hopefully this is not repeat. This next question won't repeat anything that has already been said. But what is that feeling that you guys get from going through the process? Like, is it exciting at every turn? Are there moments where you get a little frustrated? And how do you overcome them?
I'll start off. Well, at least going through school, and since I'm still in school, there's a lot of times that I cry while I'm doing homework. But to be honest, it's rewarding later. But I sometimes wonder, why did I get myself into this career, and why am I still going through school to go get another degree for the career I'm already in? But I know that in the end, it's going to make me a better engineer, even though I might not necessarily see the outcome right away while I'm doing homework or doing a program or a project at work. But I know that, okay, just give it some time, take a break, maybe walk away from it, get a drink of water, maybe go listen to something else, and then come back, and then I'll be able to solve that problem. And I know that at least with a lot of times with my side of the industry, we have to debug a lot of code, and a lot of times it's not straightforward what you're going to go look for. And so you have to go through, keep trying until one of the solutions actually works. And with that, I know that there's sometimes that I wish that I switched careers, but in the end, when it works, you're so excited, and then you're still crying because you're crying of tears of joy and not just tears of stress.
Yeah, before Tony answers, what you guys do is so important. So, I could understand how, intense it could be, because it's so important that you get it right. And also, that is common in STEM as well, where you do have to problem solve, and sometimes the problems don't come immediately, but you have to take your moment and then keep going. Tony, if you want to answer.
Sure. Well, I can tell you that from the time I was in school to now that I'm an engineer, there is a cyclical thing when it comes to engineering and to the STEM field as well, that when you know how to do a problem, you just do it, you're fine. But then when you're struggling and you don't know how to solve the problem, and then you start scratching your head and Googling how to solve this and reading textbooks and asking friends, the same thing happens in engineering life. There are many times when you don't know how to implement this specific solution, what is wrong with the circuit, how to make it work. And I can tell you that those times, at least for me, when you struggle and you work hard to actually learn it, once you learn it, you realize, well, this isn't as hard as I thought it was going to be. This actually makes sense. And when you learn it, it just becomes part of you, and it's something that you know. And the next time when you encounter something like that, it's going to be much easier. And that same thing happened when I was taking some classes in school. It happens now that I am an engineer, and it is very rewarding once you solve the problem, once you see that piece of equipment in an aircraft flying, and you are like, well, I helped. There is that little electronic in that aircraft that I was a part of, and I figured out what was wrong. And even though I struggled through it, it's very rewarding once you find the solutions.
Nice. So we did have a question come in. Someone asked, what aircraft did Collins Aerospace produce? Any that we would be familiar with, or just even if for those of us who are novice to the field, some cool names that you can throw out there.
Do you want to take that one, Zaire?
Sure. Well, with Collins Aerospace, we do not produce aircraft. We do almost everything else on the aircraft. With us, we do a lot of the electronics. We do the seating. We do, and then our partner they're in our company, in our global company. They do the engines. We also have people that do the radios. Then we have another group that does a few other aspects of the aircraft as well. And in the end, we do almost the whole aircraft, but we don't actually manufacture any of the aircraft. And a lot of the aircraft that you might see flying, like if you go to the airport and get on the airplane to go somewhere, a lot of that electronics that that the pilots are using are us. So the little area that Tony, if you can go to that slide real quick in your electronics area, the electrical engineering. Oh, yeah. So in this section where you see the pilot's hands, all of that area is done by us for the most part. There's a few other companies that do produce this part of the aircraft that we compete with, but majority of most of our United States aircraft and some of our other countries, we do use this part. And especially where the pilot's hand is, there's like a little page or like displays. That's personally what I work on a daily basis. I work on that area where you'll display where you're heading into. I don't know if Tony wants to talk a little bit about what he works on there.
Nice. What advice would you give as far as courses or any extracurriculars that students should look to if they want to go into this career path?
Well, I can speak for myself. I think sports, particularly tennis for me, made a big difference because it showed me discipline. And when you work hard in something, where it is sports, where it is school, then you're like making yourself learn something new, making yourself be better at something. And that discipline of, okay, I am hitting a forehand and I'm not hitting it good. I need to learn how to improve my forehand or my backhand, or that same principle applies to school. This equation is not working for me. I don't know this calculus method. I don't know how to take derivatives. Well, you just gotta try hard and learn that discipline. And at least for me, sports was a very big motivator on how to learn that discipline to then challenge myself when I was in school. So that is something that can speak for personal experience.
I love that.
And for me, I had a hard time learning in school. So I didn't disclose this earlier. I have a learning disability. I have dyslexia, and I had a hard time learning how to pronounce certain words and certain ways of pronouncing the saying of the letter, like ahs and a's and all of that. But for me was I knew that the bigger picture was to one day work in the space field. And for me, I just never wanted to give up, even though the hurdles were all the way there and my bumps along the road were not very easy. But for me, I just kept doing that. And then also, I found different groups and different organizations that I got a part of. For me, I got a part of the National Society of Black Engineers, and they were able to help me through that journey, as well as they even have a junior level where if you're in high school now or even younger, you can get a part of that. And also, I got involved with the Society of Women Engineers, as well as AIAA, that's an American Association of Avionics and Astronomics. And there different organizations, at least, that I got a part of that kept making me motivated to keep going into the field I'm going into.
Alrighty. Wow. So before we wrap up and I ask you guys to say your parting words, I definitely want to just say that this has been like an amazingly diverse panel that we've had with the two of you. Zaire sharing about your learning disability, definitely for youth that are watching and hear that, that's very encouraging that no matter what, they'll be able to pursue careers in STEM. And Tony, usually we don't associate certain activities like sports for guys or cheerleading for girls with STEM. And, that's really great that you can show that variety and diversity in being able to have an interest in that and do that and be in the STEM field. So you guys can share anything else that you would like the students to know, and then we'll wrap up.
Well, Carlin, I just want to thank you and Tokiwa for having me and Zaire here to share a little bit about our journey as engineers.
No problem.
And then Tony, can you go to the next slide, please? And I want to end off this. So this is my graduation picture from Tuskegee University. And you can see that there's two arrows, and I'm not on the straight line path because we're not always on the straight line path in our life. There might be times that we might take another turn. We might be in the middle. We might turn another way. But at the end of the day, you never know what is around the corner. It could be everything. It could be nothing. You have to keep putting one foot in front of the other. And then one day you'll look back and you realize, I'm an aerospace engineer. Thank you.
Well, I just want to thank everyone for tuning in the cafe. I want to thank Tony and Zaire, and I want to just acknowledge that Tony is on our advisory board. And so when he was like, can I do it via cafe speaker? We're like, sure, you're an engineer. So thank you so much for making time to do this. I hope that everyone learned a lot. I'm an engineer by training, so I'm always like, yes, engineer, you can speak to us all the time. So thank you so much. I learned so much. And those of you, be sure to do the simulation. I do have one question, Tony, for you about the bad things can happen. So when I was getting my engineer degree, I was a chemical engineer, and we had to take intro to electrical engineering. And I had a few circuits, have a little smoke and fire. Is that one of the bad things that can happen while you are encouraging kids to do the simulation instead of playing with circuits and batteries? And
that is one of the not so bad things that could happen, because if you connect a light bulb to a battery directly, it could explode, and that could be glass, and it could get to your eyes or your face. So you really need to be careful not to apply more volts and more current than a light bulb can take, for example. And that's just one little example that I can think of.
so fire is not the worst thing. Things explode. Okay.
There are scenarios in which you could get worse things than fire, yes.
Wow. Well, I definitely learned something else. Well, thank you so much, Tony and Zaire, and thank you for everyone that tuning in live or on our YouTube channel. Have a great evening, everyone, and be sure we'll have our next cafe 2 weeks from now, right, Carlin? I think 2 weeks now, but look at our Facebook, Instagram for the next cafe. Have a great evening, everyone. Thank you for tuning in.